Okay, I'm going to talk about briefly the benefits of using spherical coordinates, because if we introduce this complicated machinery, it should help us in some way. So what it should do is it should simplify certain regions in space, right? Because, for example, in cylindrical coordinates, we knew that we could have just written this as x squared plus y squared equals r squared, and z, it's anything. But if we used, oh, not r squared, let me call this 1. R, because the point of r is we'll introduce r. So, but when we introduce r equals square root of x squared plus y squared, this equation just becomes r equals 1. And any z and any theta. And so that's a 1D equation. So you can think of it as simple as possible. Right? So we started with something complicated, 2D, and we reduced it to 1D. So spherical coordinates should do something similar. So for spherical, you would hope that the sphere would benefit from spherical coordinates, and it very much does. So the sphere is x squared plus y squared plus z squared equals 1. And well, you can, if you're not sure why it's z squared too, just think of it as the length of the position vector squared equals 1. And the position vector, of course, is x, y, z. And notice that it's a 3D equation. So it's not simple a priori. But now when you use spherical coordinates, which I'm gonna use one representation as rho sine phi times cosine theta sine theta. Remember, it's a circle within a circle, rho cosine phi. Then if you take the length, oh yeah, this is x, y, z. So then if you take the length of this, well, you get rho sine squared theta, or I'm sorry, rho sine squared phi, rho squared sine squared phi, times the length of this unit vector, which is 1, plus rho squared cosine squared phi. And so this is just rho squared. So that's what the length of x squared, y squared, z squared is. So that means the sphere is also equivalently given just by rho equals 1, the unit sphere. So we've reduced it now to a 1D equation. And so we've simplified the sphere to as much as possible. And if, like, for example, if you have two concentric spheres, I would say it's even difficult to draw, right? Right, because I could try to do a small one like this and do kind of a larger one like this, but because it's 3D, I have to somehow indicate it's 3D. And this is just messy. But in a good coordinate system, we can represent these things in a much simpler way. So for example, if this is radius 1 and this is radius 2, then we can just plot this in, for example, the RZ plane as rho equals 1, rho equals 2. And so it's much simpler. So 2D representation is simpler. I could have plotted this also just in a 1D sense, but I think plotting a 1D object in 2D space is more representative because really, if I just did 1D, it would look like this. I would have the real line, and I would have row equals 1 here, and I would have row equals 2 here. This is not, so 1D is not, 1D plots are not illustrative. So, and I would use 2D plots, RZ. So let me just show you another one, another service where it's also very simple. We can think about the cone. Z equals the square root of x squared plus y squared. So we already knew this was simple and cylindrical, right? Because this is just z equals r. If I plot this in the RZ plane, then it's just this line, right? And if I were trying to draw this in 3D space, I would have to, again, make things 3D, and 3D is always pretty messy and not my recommendation. So this is the cone in 3D. So this is cone in 2D, and but now if we do spherical, it's actually tremendously simpler. So remember, z equals, let me just draw the diagram again. Z, r, phi, remember, is measured from the z-axis. So z is rho cosine phi, and r is rho sine phi. Now, what you do is you just plug this in to the equation, and so then you get rho cosine phi equals rho sine phi, and you just cancel the rows. You get cosine phi equals sine phi, and if we just refer back to the unit circle, let me just put a phi here. We'll recall that 45 degrees is when these two things are equal. And that's just pi over 4, right? So that means phi is pi over 4. And let me just comment, why did I discard the other solutions? It's because phi lives in 0 to pi. That's its range, because if I refer back to the diagram of the north and south poles, you can see that 0, phi equals 0 and 0 and pi, this covers everything, right? Because if I rotate everything else in theta from 0 to 2 pi, we've covered all the points, right? So if I extended phi, this would be double counting. If I added a delta to phi, this would be double counting your points. And that's not good for a coordinate system. So we just restrict, when we're doing spherical coordinates, we restrict phi from the plus z-axis to the negative z-axis. We don't let it cross over. Okay, so that's why I discarded the other ones. Okay. And so we've now reduced the cone is just given by phi equals pi over 4. And again, this is a 1D equation. So it's as simple as possible. And when you're doing integrals and stuff, very simple things like this are nice because it means you can either put it on the outside. So constant limits go on the outside of iterated integrals. And the more constants you have, like let's just say everything else was a constant, then that would mean you could separate it. Well, not separate it. It just means that your complexity would be reduced a lot. Okay, so one more thing I want to mention is if you have x squared plus y squared and z squared show up together, you should think spherical. Cylindrical will probably work too, but usually not as well. Cylindrical, okay, but not as good. And Cartesian XYZ is just bad. Do not use it when you see sums of squares. So, for example, we know from x squared plus y squared plus z squared equals 1. We see that x squared plus y squared, we see the z squared, we should immediately think spherical. This is the equation of the sphere, so we were right on the money. If we saw z equals x squared plus y squared, we see now x squared plus y squared, and we see z, which is the square root of z squared. And so you should think spherical. And how well would we do? Well, this simplified down to rho equals 1. This simplified down to phi equals pi over 4, so that was pretty good. And let me just go over one more. So what if I had z equals the square root of 16 minus x squared minus y squared? Well, without thinking, I just see that x squared plus y squared. In that case, there's minus signs in front of both. And then I see the z, square root of z squared. And this was minus x squared plus y squared. So I should immediately think spherical. Well, if you do spherical, this is actually, if you square both sides, this is z squared equals 1 minus 16 minus x squared minus y squared, or 16 minus r squared. And so then this is z squared plus r squared equals 16, or rho squared equals 16. So we simplified it down to rho equals 4. Right? So just this heuristic of r squared and z squared appearing right next to each other, or in similar places, this will help tell you to use spherical coordinates. So, like one thing you'll see on your homework, it might look like you might have integrals with weird looking limits from the integral of square root of x squared plus y squared, and then you might have something like 16 minus x squared minus y squared. You should immediately think spherical coordinates because you see, and this is from DZ, and there'll be more, and there'll be more stuff. But you should think spherical because you see z and square root of x squared plus y squared. Okay, hope this was helpful. Thanks for watching.